Welcome to The Explainer. Today, we're going to break down 3 ideas in physics that sound super similar but are actually worlds apart: position, distance, and displacement. Nailing these is, honestly, the key to understanding pretty much all of motion. Okay, let's just jump right in with a little brain teaser. Picture this. You go for a 10-mile run, a big loop, and you finish right back at your front door. So how far did you go? Now, the answer seems totally obvious, right? But by the time we're done here, you're going to see there are actually 2 very different and both very correct answers to that question. So, before we can even start talking about things moving around, we have to agree on how to describe where something is in the first place. And in physics, that all comes down to the idea of position. You see, when a physicist says position, they don't just mean kind of over there. They mean a specific, exact coordinate. And to keep things simple, we usually start by picturing a number line. We pick a spot, call it 0, that's our origin, and we measure everything from there. For instance, if our origin is 0, and we say an object's position is -2 meters, well, don't let the minus sign fool you. All it means is that the object is 2 meters to the left of the starting point. Positive is one direction, negative is the other. That's it. All right, now that we know how to pinpoint a location, let's get moving. And let's start with the way we all naturally think about a journey: distance. Distance is basically the odometer in your car. It just adds. It doesn't care if you're going forwards, backwards, or driving in circles in a parking lot. It just keeps ticking up, counting the total amount of ground you've covered. Period. So, take a look at this skier. They're not taking a simple, straight path. They go forward a bit, then they turn around and go back, and then forward again. To find the distance they traveled, we have to add up every single part of that trip. So first, they ski a good 180 meters. Then they have to turn around and backtrack 140 meters. And finally, they turn again and push forward for another 100 meters. Now, the key thing for distance is you just add it all up. Direction doesn't matter one bit. So 180 plus 140 plus 100 gives us a grand total of 420 meters. That's the full story of their journey. But what if we don't care about the scenic route? What if we only want to know the bottom line? Where did you end up compared to where you started? Well, for that, physicists use a whole different concept, and it's called displacement. Displacement completely ignores the winding path you took. It asks a much simpler question. What's the shortest straight-line path from your start point to your end point? You just take your final position and subtract your initial position. That's all there is to it. So, this is where it gets really interesting. Let's go back to our skier. We know they put in the work. They covered 420 meters of ground. But after all that back and forth, how far are they really from where they started? Well, think about it. They went forward 180, then back 140, then forward another 100. If you do the math, their final spot is just 140 meters to the right of where they started. That's it. That's their displacement. All that extra travel just disappears. And this huge difference between distance and displacement, well, it introduces us to 2 really critical categories for measuring things in science: scalars and vectors. It's a simple idea, but it's a huge deal. Scalar quantities, like distance, just give you a number, a magnitude. How much? 420 meters. But vectors, like displacement, give you more info. They tell you how much and which way. 140 meters to the right. Yeah, this quote just nails it. That rightward direction for the skier isn't just a fun fact. It is a critical part of the answer. Without the direction, you don't really have a vector. So you might be thinking, okay, why do we need both? Isn't this just making things complicated? Absolutely not. Let's look at a really, really big example to see just how powerful this difference is. Just think about the Earth. It is always moving, traveling a truly mind-boggling distance through space every single year. Now check this out. After one complete year, one full orbit, the Earth has traveled almost 1 billion kilometers. That's its distance. But its displacement, a big fat 0. Why? Because it's right back where it started. And notice something else. The shorter the trip, like a quarter orbit, the closer the distance and displacement numbers get. The straighter the path, the more they start to agree. Okay, so now we're ready. We can go all the way back to our runner and finally solve that puzzle with the mind of a physicist. So, how far did you go? Turns out, both answers are correct. Your distance, the total ground your feet covered, is absolutely 10 miles. But your displacement, your overall change in position from start to finish, is 0. You ended up exactly where you started. So, if you're going to remember just one thing, let it be this. Distance is the actual winding path you travel. Displacement is just the straight line shortcut from point A to point B. And that leaves us with one last thing to chew on. Think about your own life. Maybe a scenic road trip, a project you worked on, or even your career. When is it all about the journey, the distance covered, and the experiences you